Hello everybody. Today we're going to go ahead and look at some more information on attraction forces. In the previous video you guys should have watched was on intermolecular forces. It's pretty much a review of honors chemistry. That's really where that video came from, was my honors chemistry video. But the idea was just to recap molecular polarity and how to determine intermolecular forces. I'm going to go over the bigger picture here, which is the overall thing called attraction forces. So there's a little bit more than just those intermolecular forces. So let's take a look here. I don't have a lot of notes in here. If you download the video or the notes that are on Moodle, well, that are online, you'll find the notes to go along with this. So I have a lot of pictures. I'm going to do a lot of explaining, but I'm going to do not much in the way of writing down notes necessarily. All right, so when we're looking at substances in nature, the substances are held together by attraction forces. Everything in nature is held together by attraction forces. Your body's held together by different types of attraction forces, and the desks and tables and stuff that you don't, those are held together with a different type of attraction force. Hence why you don't stick to those and get, you move past them and you don't become part of them. All right, so anyway, what I'm getting into here first is ionic bonding. So there's different types of attraction forces. Now if we look at ionic compounds have these positive negative attraction forces, and I talked about this in the we've talked about this in the past when we talked about ionic bonding. We talked about this having a lattice structure and that there's a lattice energy here. So don't forget about lattice energy. And for lattice energy, we're going to use Coulomb's law for doing that. And that would be Q1, Q2 over R. So with the strength of the lattice structure, the strength that's holding this ionic system together is based on this equation where Q1 and 2 are the charges and R is the distance between them. So if you remember, we said that the higher the charges, the stronger the lattice energy, the stronger these ions are going to attract each other. R is the distance between them. So the further apart the ions get, the further away the center of the ions get, the weaker it is, because the higher this number, the lower the lattice energy. Okay, so we find that the smallest atoms or smallest ions and the highest charged ions are going to be the ones that have the strongest lattice energy. All right, so when we deal with ionic compounds, the entire structure, it's all positive negative attraction. The entire structure has its same type of bonding. It's all ionic bonding throughout the structure. There's no separation of a different type of charge or a different type of attraction force. Now over here we have a metal. Okay, so this would be what's referred to as metallic bonding. Okay, now with metallic bonding, what we have are, what's holding this together is the fact that you get these positive nuclei, or these positive atoms. I guess I shouldn't say nuclei because there are still electrons on here. These negative charges are electrons that are free to move around, and these would be the valence electrons that aren't held on so very tightly. So in the atom itself, there are still some core electrons in there in the nucleus, but they're staying in a position. So there's a bond that's holding these together. This is referred to technically as a non-directional covalent bond. I wouldn't worry too much about that part, but just keep in mind that the atoms are held rigidly together in this lattice, very similar to what we see over here. We're going to see in all of our solids, we're going to be talking about them being in a lattice. But the electrons, well, these electrons are now free to move throughout the solution. So we've got these electrons that are moving. I guess I shouldn't say solution because it's a solid state, but these electrons are free to move. This is called the electron C model. Electron C model. And this is what holds the metals together. So you get the electron C model. All right, so the electrons are free. This is why metals will conduct electric current, why they conduct heat very well. It's because of the mobility of the electrons. So it's different from the ionic bonding because here they're held together by these somewhat covalent bond, and then the electrons are free to move throughout the entire solid structure. So we get two different materials: an ionic compound, typically a white solid, a metallic solid, based on the fact that we have these electrons that are free to move around. It's going to be silver, it's going to shine, it's going to reflect light. Why does it do that? Because of the moving of electrons. The electrons are free to move. They're going to bounce that energy back off, and I'm not going to get into the details there, but that's really why that happens. Now down here what I have is carbon, and this is looking at a different type of force that's holding together these particles. All right, so we had ionic bonding holding together ionic bonds, metallic bonding holding together metals. Now for carbon, which is a nonmetal, so this would be a nonmetal substance, Nonmetals are held together by covalent bonds. Okay, so we have here covalent bonds that are holding these together. So the bonds that are inside here are those covalent bonds. We have covalent bonds, and if you notice, very similar to the sodium iodide, to the ionic compound, the entire structure is made up of covalent bonds. So we get a remember, covalent bonds are really strong. Ionic bonds are really strong. So covalent bonds, by the way, tend to be a little bit stronger than ionic bonds. Not every covalent bond is stronger than ionic, but most of them are. So what you have here is very strong bonds held together, holding these carbon atoms together. Now this is considered diamond, and diamond is the strongest natural material. Why? Because it has these very strong covalent bonds, and it has this tetrahedral structure, which creates a very stable structure. So between the fact that we've got the strong covalent bond and the tetrahedral structure here, creates a very strong bonding. Now, keep in mind, when we talked about hybridization, this is sp3 hybridized carbons. So each of the carbons in here has an sp3 hybridization, which gives you the tetrahedral structure. Now, if we come over here and look at this substance that I have over here, this is graphite. Now, graphite is very similar to diamond in the sense that it's carbon atoms all together. So these are all carbon atoms, and again, the bond here is a covalent bond. So we get another covalent bond on our carbon. So it's held together with covalent bonds. Now the difference here is that the hybridization is not sp3, but it's sp2 hybridization. So that different hybridization gives us 1, 2, 3 covalent bonds. Over here, 1, 2, 3, 4. Remember, if you add up the exponents, it tells you how many bonding areas. Since I have three bonding areas, so therefore 3 covalent bonds. But in this area above and below, what I end up having is a 4th bond, and that's considered that pi bond. Remember, pi bonds are above and below, and those sigma bonds are the bonds that are in between the two atoms. So these would be all sigma bonds. There's no pi bonds in the diamond. In graphite, you have pi bonds above and below the internuclear axis, and you have sigma bonds in between the atoms. Okay. Again, this is reviewing a little bit too, by the way, so that's why I'm going through and explaining all this. This isn't necessarily important for this chapter, but I just want to kind of recap a little bit from earlier. So what you have are these sheets of graphite that hover above each other on these pi bonds. These are very weak, while the covalent bond that holds the atoms together is very strong. And that's why graphite is very slippery. You can kind of think about it as like sliding back and forth on this cushion of pi bonds that kind of acts as a lubricant between the two layers. And that's why we use graphite as a lock lubricant, and we use it on our pencils. As your pencil rubs across the paper, it rips off these layers of graphite. Alright, so let's get back to, so here we recap real quick. Ionic bonding, and if you have it in an ionic compound, metals have metallic bonding. Anything that's non-metal, carbon, sulfur, phosphorus, I'm talking about just the elements by themselves, are going to be considered what are called covalent bonded substances. I'm going to get into the name of what these are in just a little bit. Alright, so as you saw in the last video, there's dipole substances. I'm not going to go too much into this. I want to get to the other stuff. So you got dipole substances. That's a substance that has a positive and a negative charge to it. Any molecule that is polar, very important that you go back and review Lewis structures, because you have to determine if something is polar or nonpolar. The type of attraction force that we're going to have here is a type of intermolecular force. Alright, so here we're dealing with molecules. Now we have a molecule here, such as water. Inside the water molecule is the type of bond that we call covalent bond. Between the water molecules is the intermolecular force. Now the intermolecular force is only really true for molecules. So this page really is talking about molecules here. So if my molecule is polar, then the attraction force is referred to as a dipole force. Alright, that's true for polar, but remember there's special cases where you have hydrogen bonded to nitrogen, oxygen, or fluorine. Those three elements, if there's hydrogen's bonded to any of those three elements, then you have that hydrogen bonding that exists. So this would be considered hydrogen bonding. Again, it's the same idea. Positive, negative attraction force. Positive, negative attraction force is what's going to cause these two molecules to stick together. So molecules are a little bit more complex. In the last slide we just saw when we were dealing with elements, and ionic compounds. So those other ones, really it was the same force throughout the entire structure. When we deal with molecules, there's two different types of forces. There's the force in the molecule and between the molecules. Okay, so you have dipole-dipole between two polar molecules. If the polarity is extremely strong, that is hydrogen's bonded to nitrogen, oxygen, or fluorine, you get hydrogen bonding. Down here is London dispersion. Again, if you want to recap this, go back and watch the other video, but the idea is just that you create these temporary dipoles, and again, you get this positive-negative attraction for it. Again, this would be your London dispersion forces. This is only true for nonpolar molecules. All right, attraction forces can also occur. We're going to see this in the next chapter when we get on solutions. There's something called an ion dipole force, and I didn't cover this in the last video. Okay, an ion dipole force is when you have an ion, such as sodium or chloride, is attracted to something that has a dipole. Water is an example of something that has a dipole. Even though it's extremely strong hydrogen bonding dipole, and that actually makes it even better, but either way, it's still a dipolar molecule. Attracts the sodium ions and surrounds it, and then the anion is surrounded by the positive sides of the water molecule. So because of this, the attraction force I'm referring to is this attraction force here. This is our ion dipole attraction force. Those two are attracting each other. Okay, so those are some attraction forces. So how do I know which attraction force to use? Now I modified this from the last video. This is a little bit more comprehensive for you guys at AP level to determine what attractive force should you use in a molecule. So the first thing you want to determine is if it's a compound or an element. Oops, I just realized I spelled that wrong. So we're looking for whether it's a compound or an element. If it's an element, well then it's either going to be one of three types of elements. It's either going to be a metal, a nonmetal, or a noble gas. Okay, so the attraction force between metals is going to be that metallic bonding that we saw before. Okay, if it's a nonmetal, then we're going to say that it's covalent bonding. All right, so the type of force between, so an example of this would be copper, an example of this would be carbon. Okay, now if it's a noble gas, then it's going to be something like helium or argon. Okay, it's going to fall into the category of London dispersion forces. So that's what holds together helium and argons. So that's the attraction force that's there. Now if it's a compound, you have to determine whether it's ionic or molecular. If it's ionic, then you're going to have ionic bonding. Not a big deal. If it's molecular, well now you got to get into the fact that, well wait, is the molecule polar or nonpolar? If it's nonpolar, your answer is London dispersion force. Examples of that would be H2, O2, pretty much, again you can actually have HC4 or CH4, you could have carbon dioxide. Those are all examples. Now by the way, H2, O2, NO2, those special diatomics that we talked about, these are not atoms. These are not elements, right? Not atoms or elements. These are molecules. These are molecules. So we got to keep in mind that these are molecular substances. So these are actually molecules, not elements on this side. So when we deal with H2O2, we got to think of those as actually, two hydrogens bonded together. That's not an atom or an element. That is a molecule. So keep that in mind. If it's a molecule and it's polar, well then you got to watch for hydrogen. Is hydrogen bonded to fluorine, oxygen, or nitrogen? Okay, if it is, then you would say hydrogen bonding. So you could say example water, NH3, if I could write better, HF be another example. And then if it's just dipole, that would be something like SO2, something along the lines of HCl. So those would be examples of dipole attraction forces. Okay, so it's a nice little flow chart to help you figure out what attraction force to use. All right, let's take a look at one last slide here, and that would be on some information just regarding solids. Now solids take on two different types of forms. They take on what are called crystalline solids or amorphous solids. Okay, and the difference here is that the crystalline solid has the arrangement where it repeats itself and it looks like a crystal. It's very repeating pattern over and over again. Amorphous is where they're kind of randomly arranged. A very good example of the difference between the crystalline and amorphous solid would be sand and glass. Sand takes on the crystallized structure, the crystalline structure, where the sand particles, the silicon dioxide that's in there, creates this really nice arrangement that repeats itself over and over and over and over and over throughout the structure. Well, That would be in the crystalline structure. Now if you melt it down and you cool it down quickly, right, if you heat it up and melt it, these particles are going to move past each other, they're going to slide past each other, and if you cool it down quickly, you can kind of freeze it in that moment, kind of like where the particles are not arranged properly. And what you're going to end up with afterwards is glass, and that's how they create glass from sand, is they just basically take and melt it down and cool it down faster, and you end up with glass. And you can see through glass as opposed to the solid crystalline structures. You can see that the very difference in the arrangement gives you something that you can't see through, like sand, to something that you can actually see completely through. All right, I'm not going to go through the chemistry of that, but again, where does that come from? The transparency of glass versus the opaqueness of the silicon dioxide or the sand has to do with the electrons absorbing the light energy. Okay, the light energy all gets absorbed here. In this one, the light just passes right through. Okay. Anyway, types of crystalline solids. One question they typically ask is, what type of solid would it form? It's very similar to the last string that we saw, the last, not string, but the last flow chart that I had. So again, we're going to start out with, is the substance a compound? And again, I misspelled element because I kind of copied off my original one. So anyway, is the substance an element or a compound? Well, if it's a compound, it's either going to be ionic or molecular. Again, if it's molecular, you would call it a molecular solid. Now what they're saying here, by the way, is that you're going to have a solid structure that is bonded together, and it's going to have this arrangement. We're going to always look at them as crystalline solids, right? We're going to say it's a crystalline solid that repeats itself over and over and over again in the set. So each of these solids that we're talking about, the point, all right, that crystal lattice point is going to be a molecular substance. So if we're talking about a molecular solid, the crystal point would be water. So water would be here, water is here. What's holding those two waters together would be the intermolecular force, hydrogen bonding. Now if we're talking about an ionic compound, well then we would have sodium ions here, then we would have chloride ions here. So the particles that we would have here would be ions, would be at those points along the lattice structure. For molecules or molecular substances, you would have molecules. Okay. Now if it's an element, okay, or if it's an atom, right, if we're just talking about individual atoms or elements, then we ask ourselves, is it metal, nonmetal, or noble gas? If it's metal, then we say it's metallic solid. And at each of these points, you would have a copper, 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 copper. So what would be at this point would be a copper atom. Okay, a metal atom, whatever it happens to be. And if it's network nonmetal, we refer to this as a network covalent solid. That would be a carbon would be an example of that. You could say phosphorus would be an example. Anything that's non-metal, okay, anything that's non-metal and not noble gas, all right, then that would be a carbon, and obviously the arrangement changes. I'm not going to go into all the various structures and shapes that they can have, but there are obviously carbon would do tetrahedral as we saw before. And then here you would have your noble gas. Now I'm not going to do hydrogen, but I'm going to do helium, I'm going to do argon, I'm going to do krypton. I'm not going to do hydrogen because hydrogen is really diatomic, and that belongs over in the molecular category. Okay, this is very confusing in the beginning for students to get this and understand this. I'm hoping that the way I structured this and the stuff we'll do in class will really help you. But the AP test is really kind of focusing more on this concept this year. We'll talk more about this in class, but that's pretty much it. So talk to you guys later.